This video is going to focus on orbital diagrams, and we're going to look at some of the rules that dictate how electrons fill orbitals. This is the orbital energy diagram for hydrogen. So this is the simplest orbital diagram available because hydrogen only has one electron. Notice that energy is increasing on the left-hand side. So as you go up the y-axis, energy is increasing. Each box represents an orbital. Each row represents an energy level or an energy shell. Each little cluster of boxes represents a subshell. So when we talked previously about S, P, D, and F, those are your subshells. We also noted in a previous video that the S subshell has one orbital, the P has 3, D has 5, and F has 7. So when you see these clusters of boxes, anytime it's an S, it's only going to have one box. A P will have 3, a D will have 5, and an F would have 7. The difference between this diagram for hydrogen and this diagram for more complex atoms is the fact that for hydrogen, everything on the same energy level falls in a line, has the exact same energy. For more complex atoms, you see that, like, here's your 3. These 3 were all on the same line on the previous slide. And now, for a more complex atom, each subshell increases a little bit in energy. So here's your 1s, your 2s and 2p, 3s, 3p, 3d. You also start to see some overlap between the energy levels. And what I mean by that is this fourth energy level, the 4s, actually falls between the 3p and the 3d in energy. There's a term that you should be aware of, and it's degenerate. If something is degenerate, that means it has the same amount of energy. So these orbitals are degenerate to each other. They have the same energy. These orbitals are degenerate. They have the same energy. Each one of these orbitals, so every box that you see up here, can hold 2 electrons. Now what we need to start doing is looking at some of the rules that explain why electrons fill orbitals the way that they do. An electron has a charge to it. It's a negative particle. If you take a physics class, you will likely learn that anytime you have a charge that is moving, it produces a magnetic field. So scientists were able to do some studies around this magnetic field, and they found out that within an orbital, the electrons give off 2 different magnetic fields. So they have a different spin direction to them. We say that the electrons within an orbital have opposite spins, and we indicate that with an up arrow and a down arrow. So each arrow indicates an electron. One's going up and one is going down. This led to a 4th quantum number that is called the spin quantum number. We abbreviate it M sub s, and it only has 2 possible values. You have plus 1/2 for up and minus 1/2 for down. So now we have 4 total quantum numbers. You have N, which represents the energy level. L represents the sublevel, S, P, D, and F. Within each sublevel, you have orbitals that are going different directions. For example, the P has 3 orbitals, so the ML tells you which orbital you're in. So these first 3, the ones that we described in the previous video, they get you down to the right orbital. This last one tells you which electron you are within that orbital. So that's your final quantum number. One's going to be going up, one's going to be going down. The Pauli exclusion principle is one of the rules that dictates how electrons fill orbitals. And this principle says no 2 electrons in the same atom can have exactly the same energy. Therefore, they cannot have the same quantum numbers. Every electron within the atom is going to have a different set of quantum numbers. For us, that means that when we fill these orbital energy diagrams, you must have, within each box, within each orbital, you must have one electron going up and one going down. Another rule that dictates how electrons fill orbitals is called Hund's rule. The formal version of Hund's rule says this: for degenerate orbitals, orbitals that have the same amount of energy, the lowest energy is attained when the number of electrons with the same spin is maximized. What that means is that electrons are going to fill sublevels so that as many as possible have the same spin. So when you go to fill a sublevel, like here's a sublevel, you want to draw all of your up arrows first. And you can see that they have done that here. It's up, up, up. If you put up, down, and then an up there, it's technically a wrong answer. It violates Hund's rule. So within a sublevel, draw all of your up arrows first, and then you can come back and add down arrows. The diagrams that you see here are very much like the diagrams we looked at before, but to save space, a lot of times scientists will draw them out linearly like this, so the further you go to the right, the more your energy increases. Here is the orbital energy diagram for nitrogen. Nitrogen is number 7 on the periodic table, which tells me that it has 7 protons. So as long as we're dealing with a neutral atom of nitrogen, we can say that it also has 7 electrons. So when we go to fill those electrons into an orbital energy diagram, you've got to start on the far left with your 1s, fill it up by putting 1 up and 1 down. Then we would go to the next. The 2s, we would fill it by putting 1 up and 1 down. Then we would go to the 2p. This is where Hund's rule comes in. You need to do up, up, up before you put any down. So nitrogen would have no down arrows in this 2p. If we were to do oxygen, oxygen has 1 more electron. So I would fill up my 1s with 1 up, 1 down. Then I would fill up my 2s with 1 up, 1 down. Then I would go to my 2p, and I'm going to draw all of my up arrows first. Up, up, up. I've got 1 more electron that I need to draw. It can be facing down. So I didn't draw any down arrows within that p until I had an up arrow in every box. If you will do that, you will make sure that you're not violating Hund's rule. So electron configuration is a method of writing out where all of the electrons are located. We're going to be writing this for atoms where all of the electrons are in their ground state, which means they're in their lowest possible energy. This is a portion of an electron configuration, and you're going to see that it's very patterned. The large number represents the energy level. The letter represents the type of orbital or the sublevel, so this will always be S, P, D, or F. And the superscript tells you how many electrons are in those orbitals. The arrangement of the periodic table has been set up to help us write electron configurations. Notice that this one is color-coded. Each color is going to represent a different type of orbital. This area is going to represent an S, this area a P, this area a D, and this area an F. You're going to hear me refer to these as the different blocks of the periodic table. So this is the S block, the P block, the D block, and the F block. Notice that helium is a little strange. Helium is normally listed here on the periodic table because it does act like these other elements. However, for electron configuration, all of helium's electrons are in the S block, so it makes more sense for this subject to put helium right here. So we're going to pretend like helium is there. I've drawn in helium here, and I've also labeled our row numbers. That's going to be helpful to us as we write these. We're going to start by writing the electron configuration for oxygen. When you write an electron configuration, you start in the upper left corner of the periodic table and you go through every element until you get to the one that you're trying to get to. So we're going to write the one for oxygen. I need to start up here in the upper left with hydrogen. Hydrogen is in the first energy level, so I'm going to put a big 1. Hydrogen is in the S block, so I'm going to put an S. And there are 2 elements in the 1s block, so I'm going to put a 2 here. That gets me through hydrogen and helium. Now I go to the next element, which is lithium. Lithium's here. It's in the second row, so I'm going to put a big 2. It's in the S block, so I'm going to put an S. And there are 2 elements in the S block. Put a 2. That gets me through lithium and beryllium. Now I come over to here. The next element is boron. I'm still in the second row down on the periodic table, so that's the second energy level. But now I'm in this green area. That's the P block. So I'm going to put a P, and I'm going to count over until I get to oxygen. 1, 2, 3, 4. So 2P4. That's the electron configuration for oxygen. The large number represents the energy level, the letter represents the sublevel, and the superscript represents the number of electrons within that sublevel. Recall from previous videos that an S sublevel has 1 orbital, a P has 3, a D has 5, and an F has 7. Well, every orbital can hold up to 2 electrons. So an S sublevel can hold 2 electrons, a P can hold 6, a D can hold 10, and an F can hold 14. That means that any time you write an S right here, this number can't be any bigger than 2. But you can also see that in the periodic table because the S block is only 2 elements across. The P block is 6 elements across. For a P, the largest that number can be is 6, and so forth. Let's finish up this chapter by looking at a couple of irregularities that occur in electron configurations. Let's look at the electron configuration for chromium. You would expect chromium to have argon in brackets, followed by 4s2, 3d4. But what actually happens is 4s1, 3d5. The electron that we would expect to end up in this S sublevel has shifted over to the D sublevel. The reason this happens is that these 2 sublevels are very close in energy, and so this atom is more stable with a half full D sublevel rather than with a full S sublevel. What I mean by that, the D can hold up to 10 electrons. If in some cases, when it has half of that, when it has 5, it's more stable than if it had filled up the S sublevel. This is just one example where you have something that's not exactly following the rules. And while we won't spend a lot of time on this, I did want to point out that that's going to happen in cases where your sublevels are very close in energy.